Hello, Year 10, and welcome to your next geography lesson. Today we're going to be focusing on a particular skill, looking at something called a hydrograph, and we're going to be, via that, learning some of the causes of flooding as well. So could you have a little look at the screen now? A little bit of a retrieval grid to begin with. Got 9 questions, answer all of them. Even if you're not 100% sure, give it a go anyway. The orange ones, you'll notice number 3, that means there are 3 factors to try and remember. Over to you. You've got 10 minutes to answer all of those questions. Pause the video now. Okay, good job. Hopefully you gave them all a go, because remember, you only really learn from this by giving it a go, by testing your memory, and then by checking it. If you're just not bothered, if you've left any blank, the likelihood is you're not going to remember it now either. So here are the answers. You can double check through them. You can flick back to the last slide as well on the video to check the questions, to remind yourself what they are, correct any that you've made any errors on, and we shall continue with the lesson. Pause the video now. Okay, as I mentioned earlier, this lesson is about something called a hydrograph. So could you please write the title, what is a hydrograph? Question mark at the end, underlined, with the date, read through the objectives, make sure you've got the equipment you need there. The textbook, I put most of the things from the textbook into this slide, so actually you don't really need it. However, if you have a copy of it, it might be worth having there just in case, although it's only really needed if something I say doesn't make sense, and you can go and look at that and see if it helps in any way. But fingers crossed, you shouldn't need it. So anyway, pause the video, just take you 1 minute, get that sorted. Okay, fantastic. So in a little bit, we're going to come across this concept, a key term for today, drainage density. You've come across the idea of population density before, the number of people living in every square kilometre of land. Obviously, cities, for example, are very densely populated, whereas the middle of a desert would be very sparsely populated. Drainage density is a similar concept, except it's about rivers. It's about drainage, meaning the water, essentially. The water is being drained into rivers. So it's a number of rivers in an area, to put simple. The more rivers, the more water in a drainage basin, so the higher the drainage density. And you can see there 2 diagrams, hopefully illustrating very simply the difference. So could you copy that definition, the 2 diagrams? That should take you absolutely no more than 5 minutes. Make sure you do all your diagrams in pencil, please. Pause the video and we'll move on. Okay, so hydrographs, we're going to go through them. They're important. Why? Well, the Environment Agency, people out there in the real world do use these. The data on these is recorded in stations all the way along rivers all over the country, and this data is used to predict how likely a place is to get flooded based on a storm. It's to look back at kind of storm events and floods, and people can learn from it, predict what rivers will do, and if people can predict what rivers can do, then they start to be able to manage them, which is what we're going to move on to in your next lesson. So listen to the explanation as I go through it. Obviously, as it says there, you can go back. If something doesn't make sense, go back to it, re-listen to it, try and work it out. Use the various resources you've got. I'll show you some more on the slide in a second if there's anything that doesn't make sense. Let's move on. Okay, so we've got a hydrograph here, however, it's all covered. The first thing you'll probably notice is this is a graph. It's a hydrograph, a water graph, essentially. You'll notice a blue bar chart down in the bottom left-hand corner, in fact a histogram, and a red line graph. You'll notice axes just like normal on a graph, and yeah, other than that, just looks like a normal graph. But it's a little bit more complex than that, so let's start working through it. So the first thing to note is the axis just revealed there is discharge, measured in cumex, or cubic meters per second. So if you put your maths heads on, you'll work out cubic meters is a measure of volume, and per second is a measure of speed. So this is about the volume of water and how fast it's traveling down a river. If you want a simple definition, discharge is the amount of water in a river, but it is more than that. It's also about the speed. Obviously, the higher the discharge, the more likely a river is to flood. The more likely it is that the channel is not large enough to hold that discharge of water. The second axis along the bottom now revealed, time. You'll notice on this there's no numbers. You'll see some hydrographs that do have hours measured along the bottom. This one doesn't. A lot of them don't, depending on how detailed you want to be. But here we just got the idea of time. So the blue bars, what do they show? Well, they show rainfall. Should be nice and easy to remember that. Blue bars, just like on climate graphs. Think of them as little pots of water filling up as it rains. This shows the rainfall. And what you'll notice is that the rainfall began at the very start of the graph. It gets to a high point and then it drops down, and then it stops. So this is our storm event, our rain event. This is the period of time over which it's rained. Now, obviously in this country, probably be a lot of blue bars almost continuously, but we like to keep it simple here. Most that you will see at GCSE level will just have a few blue bars at the start, and that's it. So the red line, what does that show? Well, that shows the discharge. So the axis for discharge, really, it doesn't apply to the rainfall, it applies to this red line. So you can see it goes from a low point, and we'll go back to that in a minute, and it reaches a high point, the peak discharge. Peak, remember, peak of a mountain, peak of a hill is the very top of it. So the peak discharge here is the highest point of discharge. Now, there's also, you'll notice, a peak rainfall, the point where the rain was at its heaviest and the most rain coming down. And the distance of time between those is known as the lag time. So peak discharge and lag time, two of the most, probably I'd argue, the two most important key terms here. That's why we've gone with them first. Peak discharge and lag time. The rest of this lesson after this intro bit is going to be spent explaining why on some rivers the peak discharge might be higher than others and why the lag time might be shorter or longer on some. So these are really, really important to understand this concept. So the lag time is the period of time in hours between when the heaviest rain was, when the most rain fell, and when the river was at its peak. Now, why is there a lag time? Well, there's a lag time because remember, when it rains, we're not talking here really about the water falling directly in the river. We're talking about all the water falling in the valley. And as it falls on the land, it moves due to gravity towards the river. It can move on the surface, it can move underground. There are many different ways it can get there. But regardless of how it gets there, it moves and it takes time. So that's the lag time. So when we come to explain lag time and why some are longer and shorter, really what we're talking about is the valley and the land around it and the rainfall itself and all the different things that mean that water will either travel quickly into the river or slowly. Moving on to the next one. So we call the period of discharge that rises from the normal level up to the peak discharge the rising limb. We call the other side the falling limb. Anything above that dashed line, you see that dashed line at the very bottom, the one parallel to the axis along the bottom of the graph. Anything above that is known as storm flow. A mixture of overland flow, water flowing overland on the surface, and through flow, water flowing through the ground. So all of that water that's added in, that's known as storm flow. And finally, that dashed line along the bottom there is known as the base flow. You'll notice it's exactly at the same point that the river was, or the discharge of the river was at the very start of the graph. So this is just the normal flow of the river. You'll sometimes even see it called the normal flow. So were there no rainfall, this is where the river will be flowing. And anything above that is more water added by this rainfall, by this storm event. So I hope that makes sense. Remember, the two key terms here, the really important ones, are lag time and peak discharge. We're also going to be using rising limb today, falling limb, not so much, and the other two not so much either. But you will see the terms overland flow again coming up later. So anyway, there we go. If that doesn't make sense, go back, rewatch it. If it still doesn't make sense, read the page in the textbook. There's a video there that gives you another explanation. And finally, if there's something you're really stuck on, a particular point, then email your teacher. Specific questions. So don't email me, don't email your teacher, I don't understand hydrographs. You can't not understand any of that at all, especially if you've read the book and watched the other video and done all those things. But the key thing is here, you have to understand how these work for the rest of the lesson to make any sense, because we're going to be constantly referring back to those terms, lag time, back to peak discharge and terms like that. So this is your chance to go back. If it does make sense, well done, absolutely fantastic. Let's move on. Okay, time to test your memory. I'd like you to draw a hydrograph from memory. In pencil, you're going to start with the axes, you're going to draw the graphs, and finally label any key terms, all the key terms you can remember on that graph. Try and make it look exactly like the one we've just talked through and looked at. Do it in pencil though, because in a minute we're going to be checking it, and then you can make any corrections easily. If you do it in pen and you've got half of it wrong, well, you're going to have to restart the whole thing. So get cracking with that. It should take 5 minutes from memory, please. Pause the video now. Okay, time to check. You can look through this yourself. Just check what you've got correct. Well done. Check what you haven't got correct, if there's an error or if you've missed something off, and add it on. This now is going to be your diagram in your book to go back to and revise from. So make sure it is perfect. If the rainfall bars are not exactly the same, that doesn't matter. If the discharge line is not exactly the same, it doesn't matter. They will change depending on the hydrograph you're looking at. So that doesn't matter. But as long as the peak rainfall and the peak discharge are accurate at the very top, that's really important. Anyway, over to you. Double check. Get cracking. This should take another 5 minutes at most. I want a perfect diagram in your books. Pause the video now. Okay, fantastic. One more hydrograph to copy. Now, the reason we've got this is because you'll notice there's now 2 hydrographs for the price of 1. You've got the rainfall and you've got an A and a B hydrograph. So I'd like you to copy this with the A and the B on it and with the following terms. A is known as a flashy hydrograph. We'll get to that in a minute. And B is probably a little bit more obvious why it's called a low and flat hydrograph. Copy that. 5 minutes at most in pencil again, as it's a diagram. Keep it nice and neat. And we'll move on. Pause the video now. Okay, and here's why we've just copied that, because now the notes you're about to write and the questions you're about to answer will make a lot of sense. Could you copy the subtitle? Why do hydrographs vary in shape? If you've got space above that diagram, do it. If not, don't worry, just do it underneath it. And the task is to contrast the 2 hydrographs A and B in that figure, in figure 1. Contrast. It's a command word that means say what the differences are. Simple as that. What are the differences between A and B? Talk about the 3 things here. The peak discharge. Is it higher or is it lower? The lag time. Is it longer or is it shorter? And the rising limb. Is it steeper or is it flatter? Pause the video now. Get cracking with that. Okay, so answers. A, the peak discharge in hydrograph A is higher than in B. That is contrasting language. I'm comparing the 2 things. I'm telling you what's different. If you've written the peak discharge in A is high and the peak discharge in B is low, that's not a contrast. That is 2 separate statements. So if you've written that, you need to cross that out and correct it. The peak discharge in A, in hydrograph A, is higher than B. The lag time in A is shorter than in B. And the rising limb in A is steeper than in B. So the answers are higher, shorter, steeper. But make sure you've written it correctly. Okay, so we are going to get to the part now where we really do explain why there are differences. Hopefully you've got the answers down from that last slide. You know that there are differences here between these 2 hydrographs. Now it really is about why. So you're going to start by copying that first sentence out. Hydrograph A has a very short or long, you choose, lag time because the water moves from the valley into the river very, use your common sense here, slowly or quickly. To answer that, you need to know what the lag time means. You need to remember that. So is this the water moving slowly into the river or quickly in hydrograph A? And then you're going to give me 3 reasons for this, a mixture of human and natural reasons. But there are multiple choices here you can put in. There are not only 3 reasons. There are a number of them, and they link back to last lesson and other things you've learned about rivers in the past. Now, in order to answer those 3, you're going to need the next few slides. So let's move to the next one now. Just take a note where in the video we are time-wise, so that you can come back to this point in a minute and get going with this task once we've been through the explanation coming. Okay, so this table here is going to help you to answer those questions. Now, I'm not going to read through all these now. What we're going to do is I'm going to talk about them one by one on the next few slides. So this information is here just as a quick, nice summary for you, and this is going to help you to answer that question. At the bottom, we've got some definitions of a whole ton of key terms that are in those sentences, just to make sure you understand what they mean. So we can come back to this in a minute on your own and read through it. Okay, we start with basin size or drainage basin size. Now, the key here is, as hopefully you can already tell, the drainage basin on the left is very small and the one on the right is very large. Now, the drainage basin on the left is going to have a more rapid water transfer. You're going to see that term come up a lot, meaning the water can move more quickly into the river. Why? Well, if I put an X there and an X in a similar place on the other drainage basin, so we've got rain falling on those spots. In order to get to the river, the water does not have to travel that far on the left, whereas on the right, it's got a significantly further distance to travel. So the water on the left is going to get into the river much more quickly than the drainage basin on the right. So the drainage basin on the left is going to have a much higher risk of flooding. It's going to be a more flashy, quick filling hydrograph. The peak discharge is likely to be perhaps a bit higher because of the shorter lag time it takes for the water to get into the river. And that's basin size. So drainage density. You can see here now, back to that key term you wrote about earlier, to remind you, the diagrams there hopefully do remind you, a high density means there are more river channels in the drainage basin, whereas on the right we don't have as many. The drainage basin on the left, therefore, is going to find that it can fill with water a lot quicker. If I put, let's say, a cross here, hopefully you can see that in blue, and on the drainage basin on the other side in the same place, there are a lot more rivers on the left flowing to that point than there are on the right, meaning that there's likely a lot more water traveling past that point, and it's going to get there very quickly. Again, if I use an example, let's put a cross here, top left there of the drainage basin, and across here, you can see that on the high density, it's almost practically on the river already, whereas on the low density, this is going to have to travel either across or through the land over a much longer distance to get to a river channel. So again, it's about time. On the drainage basin on the left, it's a lot quicker for the water to get to the river, therefore a more flashy hydrograph. Rock type. So on the left here, if I have water falling here, this water is going to hit this rock, this surface, and it's just going to pool on the surface. It cannot travel through because you can see the particles making up that rock are a lot more compacted together. That is impermeable rock, whereas any rain falling on the right here can move through these holes, these pores and these cracks in the rock, and it can make its way through much more easily and soak into the ground. So on the left, we're going to see a buildup of water on the surface. On the right, we're going to see the water soaking into the ground. Now, where does water move quickest? Water moves quickest on the surface of the earth. This water is going to rush off into our river really quickly, whereas the water on the other side is going to spend more time working its way through the soil and through the ground, through the rock, and it's going to be much, much slower. So impermeable rock is one of our reasons why the water will get to the river quicker and it will fill up quicker, meaning that the lag time is shorter. So land use is very, very similar. Any water falling over this settlement here is going to pool on the surface, not because of an impermeable rock, but because of an impermeable human surface. Tarmac, concrete, things like that are going to mean that the water pools and it moves very quickly down into drains, and those drains are going to take the water really quickly and dump it straight into this river here. However, over here, any rainfall that falls is going to soak in to this soil, and it's going to take a much, much longer time to travel slowly and slowly via gravity and eventually make it into the river. So again, on the right, we've got a flashy hydrograph where urbanization has occurred, where people have built, and on the left, where we've got a more natural landscape, the water is going to take a lot longer, so we're going to see a much lower and flatter curve on our hydrograph. Relief, bit of common sense here. Any rain that falls onto these steep slopes on the side of this V-shaped valley, the upper course of a river, it's going to very rapidly fall down that slope straight into the river. So again, we're more likely to see the lag time being very short and the peak discharge therefore perhaps being higher. Whereas on the right here, any water that falls onto these slopes, well, it's going to have to travel slowly across this flat floodplain and this flat valley side, and it's going to take a lot longer. So again, you're seeing a theme here, I hope. A lot of this is about the speed of the water getting into the river, be it because it can't soak in, or in this case, because the slopes allow the water to move faster, or the steep slopes do. Soil moisture is exactly the same again. On the left, we've got saturated soil. We have puddles, so as the water falls, it cannot soak into the ground, so we get more puddles forming. This water on the surface, you see it on the school field after periods of heavy rain. You see puddles building up. That's when the field ends up getting closed. Why? Well, because the ground is saturated. It is full of water. This water, therefore, is going to move on the surface of the earth. It's going to move quickly off into rivers, and it's going to fill them up much more quickly. Whereas over this side, any rain that fell on this soil, this particularly dry soil, it's going to soak in, and it's going to move through the ground, and it's going to take a lot longer to get to any rivers. Remember, this soil will also hold on to a lot of that moisture. It'll retain it within it and absorb it into the soil and trap it so it cannot move at all because it's so dry there. So that's how soil moisture, obviously caused by heavy rain. Okay, and the last one I think is very, very much common sense. Heavy rain, intensity of rain. If there's heavy rain, it's going to fill up a river a lot faster. There's going to be a lot more water to enter it quickly and increase the discharge rapidly. Whereas if there's just drizzle and light rain, it's not going to. Simple as that. You can also see there I've put the picture of saturated ground back again, because obviously there is a direct link between those. The heavier the rain, the more likely it is that the ground will become saturated as well. So those two things link together quite nicely. Okay, on the next slide is going to be some of the answers to the task that we started with. So if you haven't done that yet, pause here, rewind back to when I told you to record and write down the number. And it's the slide with the A and the B hydrographs and the question. There was a little copy and complete first paragraph, and then you had to pick 3 of these. And remember, I want at least 1 human and 1 physical cause here, factor, to explain in as much detail as you can. Pause the video now and get cracking with that. Okay, so hopefully you've spent a bit of time going through all of that and writing those answers, and here's your chance to check. So the copy and complete part, hydrograph A has a very short lag time, so the distance in time between the peak rainfall and the peak discharge is there, and that is obviously much shorter than if I were to draw the lag time in yellow for A to B. So it's a short lag time because the water moves from the valley into the river very quickly. And all of the factors then are explaining why is it getting there so quickly. And I'm going to give you a few ideas now. So here we go, possible answers. And I say possible, I stress possible because this is only 3 of them, and you know there's many more than this. But use this as a benchmark for the level of explanation that I'm trying to look for and you're going to try to aspire to. In bold are all the various key terms I've used. So let's read through the first one. One reason for this could be that the ground is made of impermeable rock, which does not let water infiltrate or pass through it, increasing the overland flow, so the water reaches the river quickly and the rising limb will increase rapidly. Notice I've started with my main factor, impermeable rock. I've then gone on to explain what that actually means, the fact that it doesn't let water pass through it, using a key term, infiltrate. I've then gone further, that's not it. We can then explain, remember, we've got to get to the river. So it increases the overland flow, meaning that the water reaches the river quickly. And then I've dropped in a key term from the hydrograph, because we're explaining a hydrograph, so we need to link it back to that. So the rising limb will increase rapidly. So all of that together, if you haven't got an answer of that quality, you can copy that down. Absolutely, you can just have that for free. But if you've done a good job, well done. If you need to just make a few corrections, do so. Otherwise, you can have that and jot that down. And the same goes for the other 2. So a second reason could be that urbanization has occurred and people have built on the floodplain. Man-made surfaces like tarmac do not let water infiltrate, pass through them, increasing the overland flow, so the water reaches the river quickly and the rising limb will increase rapidly. You'll notice it's exactly the same as the first one. Just the beginning bit's different because it's a different factor, but as we established, some of these factors have exactly the same reason. Impermeable rock and man-made surfaces do exactly the same thing to water. Third reason, though, I went for something a bit different. A third reason is a small drainage basin, which means that the water has a shorter distance to travel from where it falls in the valley to the river, increasing the discharge quickly. I could have actually put there as well to improve that, not just increasing the discharge quickly, but shortening the lag time. There's another way to link to the hydrograph. So I could put at the end there, increasing the discharge quickly and shortening the lag time. So you can copy any of those you need to. You can check your answers as well to see if your other ones are at the same detail. If not, see if you can improve them now. And this is a point where emailing these answers to your teacher, this is exactly the kind of thing I and other teachers would like to see. So feel free to email us your answers here, and we might even be able to provide you some feedback if we can. Pause the video to do all that, we'll move on. Okay, and the final thing I'd like you to do is to spend 7 minutes answering these 2 questions. They pretty much cover what we've done today. There's not that much else that AQA are likely to assess you on other than that. The key thing here, though, is put all your notes away. If you need to turn over in your book, do so. I want this to be now from memory. Let's see how much you can remember from this lesson. There's been quite a lot to take in, so let's see how much you can remember, and then we'll spend a bit of time checking. So there we go, 7 minutes, answer those 2 questions. Pause the video and we'll go through the answers. Okay, so some answers here. Make sure for the first one you've got 3 differences. Make sure that you've referred to the figures. Make it really clear which hydrograph you're talking about. Hopefully you're using some key terminology now. You're using terms like lag time, rising limb, peak discharge, and terms like that. But read through those answers and they'll give you the answer there. And B, well, there's only so much they can say here on the mark scheme, but in order to get 3 or 4 marks, these need to be complete, clear sequences of information. It needs to be linked statements, not just simple partial points. If you go back to my examples, you'll see examples there of 3 to 4 mark answers. If you just said, for example, one thing that could cause it is impermeable rock, full stop, I mean, that's probably not going to get you even 1 mark. It might get you a mark if you're lucky and you scrape it and you do a few different points, but you need to hopefully be able to explain it a lot more than that. So basically you can go back and look at that, read through the model answer there, which gives you a bit of context, and by all means you can send this to your teacher as well. This is something else that we'd love to see, your ability here to do these exam questions. Anyway, on that note, that's the end of the lesson, so take care, have a lovely rest of your day, and I will speak to you soon. Goodbye.